Let us look at important characteristics of capacitor. Let us look at important characteristics of capacitor. We start with first important characteristic. Write down that point, all of you. Write down that point. A capacitor, first point. A capacitor is open circuit to DC. A capacitor is open circuit to DC. Open circuit to DC. Okay, what does it mean? See, I of t is equal to C dV of t by dt, right? Yes or no, all of you? All of you agree? Okay. Now, if V of t is DC, V of t is DC. DC means what? What is the frequency? Zero. Zero frequency means what? Low frequency. Yes or no? Zero frequency means low frequency. Then it implies I of t will become, because if it is DC, that means constant, derivative will become zero, then it is zero. Current zero refers to what? It's nothing but open circuit. That is why a capacitor is open circuit to DC. Understand all of you, okay? Now, it indicates that at low frequency, it is acting like open circuit. That means open circuit means what? Open circuit means what? It is blocking the signal. Yes or no, all of you? It is blocking the signal. It's not passing the signal, it is blocking the signal. So low frequency signals, usually the capacitor blocks. High frequency signals, usually the capacitor passes or allows. Therefore, you can write that the capacitor blocks, please write down. You can please proceed along with me. You can please proceed. The capacitor blocks low frequency signals. And passes high frequency signals. Please write down that. It's a very important point. So that is why we use all these capacitors in filters. So you know the filters usually, applied for blocking the unwanted signals, yes or no? Or passing the wanted signals and blocking the unwanted signals. So therefore, you can use the capacitors in filters application based on this particular point. The capacitor blocks low frequency signals. It's very clear. Low frequency, DC is low frequency. It is blocking open circuit and passes high frequency signal. The first important point to be remembered in the case of capacitor. The second one is, which is very important, useful in the transient analysis. Without the second point, you cannot really, go ahead in the case of transient analysis. You cannot really understand that. Okay. So let us look at what is the important characteristic of a capacitor. Second important characteristic. The voltage across capacitor. Write down. All of you please write down. The voltage across capacitor may not change instantaneously or abruptly. Both are same. Or suddenly. Yes or no? Abruptly, instantaneously, suddenly, all are the synonyms of suddenly changing. Remember all of you, you must always use the term may not. Okay? You must not use like cannot, shall not, will not, does not. No, you can't really use that. I'll come to that. Why we should not use those words? Why we should use only may not? I'll come to that point. I have a detailed discussion on that. Okay. But as of now, you please take it for granted. You please take it for granted that the voltage across capacitor may not change instantaneously or abruptly or suddenly. Okay. So look at this. I'll give you time again. I think all of you noted down this. First look at this. Then we will, okay, we will give you some, I'll give you some time to note down the things. Okay. Look at this. You know that I of t is equal to C dV of t by dt. Let us try to justify this particular statement. Understand all of you, okay? Now, can I write this C into V2 minus V1 by, what is this? T2 minus T1. Yes or no, all of you? dV by dt can be written as what? Change in voltage by change in time. That's it. Now, for example, in zero time, I would like to change the voltage across the capacitor from some 2 volts to some 5 volts, let us say. Do you understand? I would like to change the voltage across the capacitor from 2 volts to 5 volts. In which time? In zero time. Understand all of you? Zero time is nothing but what? Instantaneously, abruptly, suddenly, all are same. That is nothing but zero time. So what is happening here? This entire component, if you look at this value is becoming, because denominator is becoming 0 here, it becomes infinity. That means current is becoming what? Infinity. So what does it mean actually? What is the interpretation of this particular case when you are trying to change 2 volts to 5 volts in zero time, it becomes infinity? What does it mean? It means that if you want to change the voltage across capacitor from one value to other value in zero time, the current required to be passed through the capacitor is infinite. That means you need to send infinite current through the capacitor in the time 0 to change from one value to other value. But infinite magnitude in zero time is always called what? Ideal impulse. Yes or no? The name itself is saying that ideal impulse. Ideal means which is not practically possible. Which is not practically possible. That is why we give a statement. The voltage across capacitor may not change instantaneously. I'll come to this point, may not change again. Okay. I'll come to this point. So the voltage across the capacitor may not change instantaneously because current through the capacitor required to change that voltage in zero time required is infinite, nothing but ideal impulse, which is practically impossible. Understand all of you? Okay. So please note down this. First you note down this. I'll just explain you. I will just explain you the points, important points. First you please note down this quickly. Hope you have noted on that. Now look at this. Hope you have noted on this. It's a very important point. Right of this. From the above expression, it can be understood that to change the voltage across capacitor, please write down, to change voltage across capacitor from one value to other, in zero time, the current through the capacitor required is the current through the capacitor required is infinite. In bracket you write down ideal impulse. In bracket you write down, what is that? Ideal impulse. Understand all of you, okay? You write down in bracket, that is ideal impulse. Understand all of you? That means what? Actually, if you can really send ideal impulse current through the capacitor, no doubt, the voltage across the capacitor may change instantaneously. Understand all of you, okay? That is why I use the word called may or may not. Because we do not know. We do not know because we are dealing with the circuits of ideal condition, not practical condition. In our problems, you know very well, the first day itself, we have assumed that all elements are ideal. In the network analysis, the first assumption to be made before we solve, before we analyze, the first assumption to be made is what? The entire circuit is ideal. All the elements present in the given network are assumed to be ideal. Understand all of you, okay? So in such cases, now what will happen if you are really able to pass ideal impulse current? Because there are certain problems involved, okay? Sending ideal impulse current through the capacitor also. I'll discuss all the problems later. Okay? Now it's very clear. So therefore, you can note down that note. If IC of t, if IC of t, what is IC of t? Let me draw it here, okay? Say this is C, this is VC of t, this is IC of t. Understand all of you, okay? This is Q, okay? If IC of t is finite, then VC of t may not change instantaneously. Okay? You already know that Q is directly proportional to V, yes or no? Now all the statement what you use for voltage can also be applicable to the charge. Understand all of you, okay? So therefore, voltage across the capacitor may not change instantaneously. Similarly, the charge, okay, the charge of capacitor, the charge of capacitor may not change instantaneously. You can comfortably use that statement. Understand all of you, okay? Wherever you use the voltage, there you can use charge also, because the charge is directly proportional to V. Charge is equal to C into V. C is constant. Yes or no, all of you, okay? C is constant value. Therefore, you can use it. Now, here also, voltage across the capacitor may not change instantaneously. That means here the charge Q may not change instantaneously. This is the first condition. Now, you can write if IC of t is infinite, that means ideal impulse. Please note down that clearly. Ideal impulse. Write down all of you. Ideal impulse. Ideal impulse. Okay. When it is ideal impulse, okay, then VC of t, nothing but what? Q, may change instantaneously. Getting all of you? If I send this very, very important point, I'm telling you, there are some special problems asked in the GATE and even other competitive exams based on this particular concept. Many of the times we people miss the ideal impulse current passing through the capacitor. That point we generally miss. We always remember simply the voltage across the capacitor may not change instantly. That's it. But I'm telling you the problems are coming in a different way. Unless you know this concept, you cannot answer. Even in the interview also, the professor across the table, okay, whenever the interview that you face, people will try to test you whether you are really aware of this particular one or not. It's very, very important concept. Okay, it's a fundamental concept, nothing new in this, but that fundamental usually we miss it. Okay, so please note on that. Okay, so voltage across the capacitor may not change instantaneously provided current through the capacitor is finite. Voltage across the capacitor may change instantaneously provided current through the capacitor is infinite, nothing but ideal impulse. Yes or no? Now, another important point to be noted here is that, okay, current through the capacitor may change instantaneously. Current through the capacitor may change instantaneously. Current through the capacitor may change instantaneously. You can write down that. Here also you should write only may. You cannot say current through the capacitor cannot change instantaneously or does not change instantaneously or must not change instantaneously. Please do not use such kind of statements. Always you must use may or may not. Understand all of you, okay? Hope you understand why I am using may not and may here. Because I do not know. Because I do not know what is the current flowing through the capacitor. Here, suppose if I use, I can comfortably, if somebody is mentioning that current through the capacitor is finite, now you tell me, then you can say voltage across the capacitor cannot change. Because they specifically mentioned what is current through the capacitor. If current through the capacitor is found to be infinite, that is ideal impulse, you can confidently give, yes, voltage across the capacitor can change. Understand all of you? Since we are not sure about that, we are using carefully that word. It's a precaution, okay, so that there is no contradiction all the time in your statements. That is why we are supposed to use only may or may not. Understand all of you? I'll come back again why we should use may in case of current through the capacitor, okay? I'll come back to that again. When I discuss inductor, I'll tell you that point, okay? Now, some examples I would like to show you here based on this particular one, okay? Now, which of the following is acceptable? Is or are acceptable, okay? First one is, this is voltage across the capacitor. I am clearly mentioning intentionally here VC of t. Okay, this is some 10 volts. This is some minus 2 volts. Okay, so this is 1, 2, something like that. It is in seconds and it is in volts, let us say. Second one is, VC of t, again it is in volts. Please note down, time t is in seconds. It is some 10 volts, let us say, some 1 second or 2 second, whatever it is, something like that. Okay, which of these is acceptable to the capacitor? To the capacitor. That's a question, okay? Example. Which one is acceptable? Which one is acceptable? Which one is acceptable? Yes, all of you. Tell me. Hope you got an idea which one is acceptable here. Okay. Let me give you. See, what's happening here, the voltage across the capacitor, it is changing from 10 volts to what, suddenly coming down to what, minus 2 volts. In how much time, Nana? In 0 time. We know that voltage across the capacitor may not change instantaneously. Yes or no? But of course, Unless you know the current through the capacitor, whether it is finite or infinite, you cannot confirm. But in the problem or in the question, if it doesn't give any information regarding the current, whether it is finite or ideal impulse, by default, you must take always it is a finite current. Understand all of you, okay? If there is any mention, okay, of current that is infinite or ideal impulse, it is okay. If it doesn't mention anything, let us say on the problem, the current through the capacitor must be taken as what? Okay, finite only. I think you understand the point. Now, looking at this particular one, you see here, what's happening here? 10 volts to minus 2 volts, it is suddenly dropping. When current through the capacitor is finite, then voltage across the capacitor may not change instantaneously. Yes or no, all of you, okay? So, is it really acceptable or unacceptable? It is not acceptable. You can also observe that it is a discontinuous function. Discontinuous voltage, discrete voltage. Discontinuous voltage is not acceptable to the capacitor. Of course, keep in mind, again, current to the capacitor is finite. The same discontinuous voltage may be acceptable to the capacitor if current through the capacitor is ideal impulse. You got the point, all of you, okay? Since he did not mention whether current is finite or infinite here, you can say discontinuous voltage may not be acceptable. May not be acceptable. Discontinuous voltage across the capacitor may not be acceptable. Understand all of you, okay? Now, what about this particular one? It is a continuous voltage, yes or no? There is no sudden fall from one value to other value. How do you recognize whether discontinuous or continuous? If suddenly falling from one value to other value, changing from one value to other value, then it is considered to be the discontinuous. But what is happening here? Gradually increasing and gradually decreasing. There is no sudden decrease or sudden increase. Yes or no? Here sudden increase, then sudden decrease, then sudden increase, like that you have. This is continuous, discontinuous, this is continuous. So continuous, since it is there, then continuous voltage across the capacitor, continuous voltage, okay, may be acceptable. Yes or no? May be acceptable. Yes or no, all of you? Continuous may be acceptable. Getting all of you? Okay? Suppose if I give a current, third one. So this is acceptable, but this is not acceptable. Third one. Suppose if I give, instead of voltage, if I give you current, now this is, let us say, IC of t, and this is, let us say, time in seconds, let us assume, some 10 amperes, and this is some minus 2 amperes. Now you tell me, what will you do? Now you tell me. What's happening here? It is changing from one value to other value, but this is a current. Current through the capacitor may change instantaneously. Understand all of you? Current through the capacitor may change instantaneously. Irrespective of the voltage, whether it is finite or infinite, doesn't matter for us. Yes or no? Therefore, okay, discontinuous. Here it is what actually? Discontinuous. Discontinuous current may be acceptable. May be acceptable to the capacitor. Understand all of you, okay? Discontinuous voltage may not be acceptable to the capacitor. Again, that is also acceptable if you are able to send infinite current to the capacitor. Discontinuous current may be acceptable all the time. Understand all of you, okay? All the time. Again, maybe I'm carefully using, I'll come back to that point. Okay? May change. That means may be acceptable. Coming to that now, continuous voltage may be acceptable. Yes, continuous voltage, there is no problem. The problem comes only when the voltage is discontinuous. Again, the current is finite. Yes or no, all of it? Very, very important discussion I'm telling you. One should have command on all these important cases. Getting all of you? Please note down quickly here. I'll give you some time. Please quickly note down. Please quickly note down all of you. So this is acceptable, right? I am just giving. Here it is not acceptable. That is why I have given here a cross mark. This is acceptable. There is no problem. This is acceptable. Quickly note down. Then third important characteristic. Then we'll go for third important characteristic. Then we go for third important characteristic. Write down the third important characteristic here. I think all of you written this. Third important characteristic here. Third important characteristic. What is the third important characteristic here? An ideal capacitor does not dissipate energy. Okay. So when is the energy dissipated? Usually only when there is a resistor component. Energy dissipation, power dissipation. That means there is a presence of resistor. So ideal capacitor doesn't have any resistor component at all. It simply stores the energy and gives back that energy to the circuit wherever it is connected. Wherever it is required, you can retrieve that energy 100% in case of ideal. Okay, that means there is no resistor component. If there is a resistor component, what will happen? There is a dissipation takes place. If there is a resistor component, then that is not called ideal capacitor. Okay, therefore, I call now here fourth one, a practical capacitor or real capacitor. A practical or real capacitor dissipates energy. Dissipates energy. A practical or real capacitor dissipates energy. So how does it look like? This is what actually the practical capacitor C, comma capital R. That means now if you can represent it by, okay, a practical capacitor, it looks like this. This is a practical capacitor. But now you are converting the practical element into ideal element. Okay, there is a mathematical model. Okay, you need to, because all elements are assumed to be ideal. Yes or no? So what is the ideal model that you can take now? Here, this is C. Now this is an ideal capacitor because you separated. Physically not possible, but mathematically possible. This is ideal now. Okay, this is a resistive component here. The practical capacitor now is represented with the parallel modeling resistor. Usually this resistance value is very, very large, as larger as 100 mega ohm, 1000 mega ohm, 10 mega ohm, something like that. Always in mega ohms. Mega ohms means what? Current is usually in microamperes. So microamperes current is very minute or very less. You call that current as a leakage current. So wherever you have a capacitor, because there is a resistor component, practically speaking, then there exists some leakage current. Understand all of you? Okay. So this is the practical capacitor. A practical capacitor, real capacitor dissipates energy, and it can be represented by, write down, and it can be represented by parallel modeling resistor. parallel modeling resistor, and it can be represented by parallel modeling resistor. Okay, this is how you can see the capacitor, and of course you can go with the series and parallel combination of capacitors. We'll see that, and then we will switch over to inductors, and after that we'll see some important problems on inductors and capacitors. Okay, so complete that quickly, and I'll go for series and parallel combination of capacitors. Series and parallel combinations of capacitors. So the four important characteristics one should remember. What is the first one? A capacitor is open circuit to DC. It blocks low frequency and passes high frequency signals. Second point is what? Second characteristic is what? The voltage across the capacitor may not change instantaneously. Okay? We have proven that if you really want to change the voltage across the capacitor, the current through the capacitor required is what? Infinite, nothing but ideal impulse. Okay? But current through the capacitor may change instantaneously. Now, third important point, an ideal capacitor does not dissipate energy. Fourth important point, a practical capacitor dissipates energy, and it can be represented by a parallel modeling resistor. Usually the resistance value is very high, Nana. So microamperes current flows. Leakage current, you call it, very, very minute current. That is why in most of the cases we neglect it, because the current passing through the resistor is very, very less. Okay. Now, series and parallel combination of capacitors. Just write down series and parallel combination of capacitors. First, let me start with series. Series combination of capacitors. C1 and C2 are connected in series. This is A, this is B. Usually in series case, when you apply some voltage V, it gets divided V1 and V2, and the charge remains same. Because in case of series, the current is same. Time rate of change of charge is nothing but current. Current is same and charge is also same. Understand all of you? Okay. Current is same and charge is same here. So charge on C1 and charge on C2 is same now here. So series combination, the two important points, instead of current we are writing charge same, but voltage divides. Hope now you understand. In parallel combination, voltage same, charge divides. Understand all of you? Okay. So what is the total charge that is being supplied by the voltage source is Q, then the same charge will be deposited on C1 as well as C2 here. Okay. So now you can see the formula. What we do here is 1 by C equivalent, or CAB is equal to 1 by C1 plus 1 by C2 plus and so on, 1 by Cn. Okay. We can use that CAB can be written as, okay, 1 by summation, because this is summation, right? Okay, summation I is equal to 1 to n, 1 by Ci. Okay. See, when you go for n is equal to 2, then CAB will become C1 C2 by C1 plus C2. And remember, the equivalent capacitance always it is less than, okay, the lowest value of, even the lowest value of, what is that? C1, C2 and so on, Cn. It means that when you connect the capacitors in series, the effective capacitance will decrease, unlike resistors. Okay. Well, now let me even take the Q is equal to C1 V1, Q is equal to C2 V2. Yes or no? Because charge is same. Therefore, I can write that from this, the voltage is inversely proportional to C. But you also know that voltage is equal to V1 plus V2. The voltage divides in, okay, divides V is equal to V1 plus V2, and the voltage is inversely proportional to C. Note on that, all of you.